So in order to efficiently compute biconnected components, we're going to use the same algorithm we did before. Given an undirected graph G, we run depth first search on it. We identify edges as being discovery edges or back edges, and then we use that labeling in order to construct a proxy graph, a helping graph, so that in this graph, we have each vertex corresponds to an edge of our original graph. We add edges in this graph corresponding to, let's call them back vertices and discovery vertices, as they correspond to back edges and discovery edges in our original graph. We add an edge if this back vertex was in a simple cycle with this discovery vertex in our original graph. And then we find in this auxiliary graph the connected components. Then the vertices that belong to the same connected component correspond to edges from our original graph that belong to the same link component. Those edges induce biconnected components. The only downside of using this approach was that we could end up adding a lot of edges in our auxiliary graph, and the number of edges in our auxiliary graph is the bottleneck behind this algorithm. If we can create this more efficiently, we will have a better runtime. So our goal is to create a better auxiliary graph, one that still maintains that if two vertices in this auxiliary graph were connected, then they'll stay connected in this better auxiliary graph. But we use the least number of edges as possible. So we're going to create it a little bit differently. So our new proxy graph, our new auxiliary graph, what we'll create, will be as follows. So we're going to keep track of when we ran depth first search. Let's say this was the first vertex we encountered, the second one, the third one, fourth one, fifth, sixth, and seventh. Now, in the order that we encountered vertices along this depth first search, we're going to insert the discovery edges as we encountered them, and I've already put them right here in our proxy graph. We'll insert our discovery edges as vertices in our proxy graph, but we're going to be more careful about when we add a back edge or back vertex to our proxy graph, what edges will be incident on it. So we're going to add them in order of when we encountered vertices. So first, at vertex 1, are there any back edges going into this vertex? And there aren't, so we're going to move on. Now for vertex 2, are there any back edges going into it? Now we're also going to maintain for these vertices, are they linked yet? So I'm just going to put a label here to indicate they are not linked yet, they're unlinked. And we'll update this as we go along. So initially they're all unlinked. Okay, so we had no back edges going into 1. Now we have a couple back edges going into 2 to choose from. Let's just say we evaluate this one first. It doesn't matter which one we evaluate first. Now we're going to add this back edge C as a vertex in our proxy graph. So I'm going to put it here. Here's our back vertex C corresponding to this back edge C here. And we're going to only add edges as necessary. So we're going to, again, go through this and see what discovery edges participate in a cycle with C. And our first step will be to, okay, given this, we've got, this forms a simple cycle with B and D. So our first step will be to add an edge from C to B. And then after that, check to see, oh, was this already linked? Well, it wasn't, so we're going to change it to be linked now. Then we add an edge from C to D. And then we check, was this already linked? If we connected to something that was already linked, we'll be able to stop early and be done. But if we didn't, then we'll have to update this and say, all right, it's linked now. Now we have another back edge, F, coming into vertex 2. And this formed a simple cycle with discovery edges, G, B, and D. So we're going to create F. Let's put it here. And we're going to add edges to our candidates are G, B, and D. So we're just going to go in this order of as we were traversing through this simple cycle. So our first step is to, first we add an edge and then we check to see if that vertex was linked already. So we add an edge and check to see if it was linked. It wasn't, so we're going to change its status to now be linked. Now we add an edge to B. Then we check, was it linked? Ah, it was linked, which means we don't need to add any more edges because everything that B was linked to, F is essentially also linked to through some slightly longer path. So we don't have to add an edge to D, for example, because we already have a path to D. So we're going to stop early. Now we're finished with all the back edges which go into vertex 2. We're going to move to vertex 3, and we've got one back edge which goes into it, and this is E. So we're going to create back edge E here, or vertex E, and this forms a cycle with discovery edges G and B. So we're going to add an edge from E to G first, and then check, was it linked? Ah, yes it was, so we don't have to continue. Again, this is just enough edges added in order to connect E with everything else that was in that connected component. Now we have no other back edges going into vertex 3. We move to vertex 4. It has no back edges going into it. Then we move to vertex 5. This has one back edge going into it, which is J. So we're going to add J as a vertex in our proxy graph. And candidate edges it should add to, we have, this forms a cycle with I and H. We're going to work our way around here. We have J to I, and we check to see, was I linked already? It wasn't, so we're going to mark it as linked and keep going. And then J to H, check to see if it was linked already. It wasn't, so we're going to keep going. And we reach the end of that cycle, so we have nothing more to do. Now we move to vertex 6. It has no back edges going into it, and vertex 7 has no back edges going into it, and so we're finished. So this is one way in which we can create this proxy graph using the least number of edges as possible in order to connect the necessary vertices of this proxy graph. So our algorithm is still the same, we just changed how we created this proxy graph. Each vertex still corresponds to an edge of our original graph. Now we just need to find the connected components of this proxy graph. Here we go. So this was that proxy graph that we created from our original graph G. This is a spanning forest of our original auxiliary graph that we had made, which had too many edges. We were just more careful about how we created it now so that we get a spanning forest. This is really the least number of edges necessary. So since we've got m vertices in this proxy graph and we have a spanning forest, this means that we have big O of m edges as well. This is the least number of edges to connect those vertices. Which means if you go back to the first slide here, this was the bottleneck to our algorithm to compute biconnected components was based on how many edges were in our proxy graph. So that means now we can construct this proxy graph in n plus m time. We can find all biconnected components in n plus m time. Because we've reduced the number of edges in our proxy graph. So this is no longer our bottleneck. This is no worse than the amount of time that we spent in running depth first search on our original graph and creating this proxy graph. We can efficiently find the connected components of this graph in big O of m time, which corresponds to the link components of our original graph. So our total running time, running depth first search on this graph, creating this proxy graph, running either DFS or BFS on this proxy graph to find the connected components, and then outputting all the connected components of this graph, which are linked components of our original graph, which induce biconnected components of our original graph. In total, n plus m time. So we can find all biconnected components really in linear time in n plus m time. This is a good example of an algorithm where we have, more than one thing going on here. We have a few different steps to this, and this is a good example of an application of depth first search and breadth first search for one, but also why we would in particular want to use depth first search for this first step. And this is because we're repeatedly finding those simple cycles, and with depth first search we can easily recreate from this back edge what other discovery edges participated in the cycle with it. And this runs in no more than however much it costs to go through our depth first search. So we can repeatedly find these cycles more efficiently with a depth first search. But this is another good example of taking an algorithm which is complex and breaking it up into different steps in order to figure out what the bottleneck of that algorithm is to identify possible points of improvement. So for us, this was identifying that this proxy graph, the one that we had created, the auxiliary graph that we had created before, had a lot of edges to it, and we could create it a little bit differently using less edges, which ultimately improved the running time of our algorithm. Okay, if you have any questions, reach out on Piazza and let me know.